bipyramidal. And then finally, we have octahedral. This is if I have 6 groups around the center atom. It doesn't matter what the 6 groups are. For all these shapes that we're talking about, the identity of the groups is irrelevant. You just count how many groups there are, think about the best way to space them out, and that gives you the name of the shape or the angles that we're looking for. So with octahedral, kind of similar to the trigonal bipyramidal, we're going to form a shape in the horizontal plane. This time it's a square. So 1, 2, 3, 4. Those 4 groups are all in the horizontal plane. And then I have one straight up and one straight down. If you look at the relationship between any of these groups, they're actually from 1 to the closest group is always going to be 90 degrees, 90 degrees, 90 degrees, 90 degrees. Same thing to the bottom, 90 degrees between any of the side groups. I can go all the way from the top to the bottom and get 180 also. So in octahedral, 90 and 180 are the angles that you need to know. So those are our basic structures. Now, from that, we then have to think, okay, well, how can I vary that? If I have 5 groups, when we think about the actual shape of a molecule, we tend to mostly focus on the atoms. And if the center atom has lone pairs, we're still going to use the same basic structure, but the lone pair is considered to be less important or something that I don't tend to focus on as much. So I usually will ignore the lone pair, but I can't do that initially. If I ignore the lone pair initially, it's going to make me get the wrong shape. I have to include the lone pair at first, decide on the basic structures that I just showed in the past few slides, and then in one position, if it's a lone pair, I'm going to remove that from the shape and see what's left. So we're going to get variations off of our basic structures that we see. Okay? So I'd like to start, and actually I'm going to, so in the next few slides, it does show all the different variation shapes that we need to know. There's a chart in the book. You need to know all of those. Okay? With 4 groups, our basic structure is going to be tetrahedral. But if I cover one group up as a lone pair, that's going to give me a new shape that I haven't said yet. It's called trigonal pyramidal. Then if I cover 2 up, it's going to give me the shape that is called bent, and so on. So those are all listed in the book. You need to memorize them, but we're going to work a few examples right now just to talk about. So I'm going to flip the lights on. And we're going to use the chalkboard. All right, so when we talk about 4 groups, our main molecule that we use as an example for 4 groups is often CH4. So if I draw the Lewis dot structure, carbon with 4 hydrogens, if you look at that carbon atom, see 4 hydrogens around it, you should automatically think 4 groups is tetrahedral. And then if I ask you, what's the angle between any of the 2 hydrogens, so it's an angle from hydrogen to carbon to hydrogen, that angle, if you look at the board, it appears to be around 90 degrees, okay? But you have to remember a 2-dimensional representation drawn on a chalkboard might not be realistic in the real molecule and how it exists. This molecule is not linear. It's tetrahedral. I need to know that. And therefore this angle, even if it doesn't look like it is, that angle should be 109.5 degrees. Okay? All the other angles are also 109.5. Because remember, we're not going around the circle on the flat board. We're in a 3-dimensional structure in real life. So, next example. NH3. If I draw the Lewis dot structure of NH3, the nitrogen has 3 hydrogens around it. But then, we know that nitrogen is supposed to have 5 valence electrons. I've used 3 of them to make bonds. So that means that there's a lone pair on the nitrogen also. that lone pair, those two electrons actually exist in an orbital that does take up space. So the nitrogen has 3 hydrogens attached to it, plus a lone pair. All 4 of those groups occupy space. They're all part of the overall shape. If I include the lone pairs, we're going to call the shape that I get from that the electron geometry. It's the arrangement of all the electrons, specifically valence electrons, around the center atom. So nitrogen has 4 groups of electrons around it. 4 groups, the electron geometry is always tetrahedral. Okay, so I have a model. Right now this is CH4, okay? But if I take off a hydrogen, now this is what the model would look like if it was ammonia. Nitrogen in the middle, 3 hydrogens around it, and then the stick at the top is my lone pair. It's just 2 electrons occupying space, but there's not another atom there, okay? But hopefully you can see the general structure of CH4 and NH3. If I just put the hydrogen on, now it's CH4, take the hydrogen off, that's a lone pair now. This is what NH3 would look like. The overall basic structure is the same. Now, when I look at a molecule, I'm usually mostly focused on atoms. Nitrogen with 3 hydrogens around it. If I ignore the lone pair, pretend it's not there, I would have expected this molecule, if I'm not paying attention to the lone pair, to be 3 groups, and that would mean it would go to trigonal planar. But if I look at this molecule, I can see the nitrogen and the 3 hydrogens are not all in a flat plane. If I actually set it in my hand or set it on the counter, I can see the nitrogen atom is actually raised up above the other atoms. If I get rid of the lone pair, remember a lot of times we want to ignore the lone pair. It does exist, but I'm going to take it off. It's occupying space up here, but it's kind of invisible. The 3 hydrogens are now pushed down. The nitrogen is above. It looks like a pyramid. And the base of the pyramid is a triangle. So while the basic structure of ammonia was built off of the template of tetrahedral, when I take the lone pair off, it gives me a different shape. We call this the molecular geometry. It's the one that you get when you take the lone pair off and look at what remains. This one's going to be called trigonal pyramidal. It's a pyramid with a triangular base. Okay? This is not as symmetrical of a molecule as CH4. CH4, I have 4 groups, and it's the same group all the way around. That's called a symmetrical shape. If everything all the way around the carbon is the same, it's symmetrical. Ammonia, though, has 4 groups. One group's different. It messes up the symmetry. Trigonal pyramidal is not a symmetrical shape. Okay? And that's going to be important in my next video when we talk about whether molecules are polar or nonpolar. So I'm going to cut off for now. My next video, I'll work some more examples and continue with this topic.